Welcome, and thank you for this opportunity to present the general theory of information and machine intelligence. This presentation is a novel integration of many aspects of computer science, genomics, and neural science. There is a lot to cover, and we encourage everyone to explore the references provided to gain a deeper understanding of this topic. The principles of the general theory of information involve infusing autopoietic and cognitive behaviors at both the component and system levels using super-symbolic computing structures. This is akin to the neocortex in the brain, integrating information from different senses and interacting with its environment using a common knowledge representation. This novel system design expands on the traditional Turing machine and pattern-based learning to create a distributed application for information interpretation and knowledge acquisition. This picture summarizes the evolution of machine intelligence used in process automation and gaining insights from data based on their patterns using machine learning. This approach is analogous to how biological systems evolved in the neocortex structure. A human genome specifies and executes life processes using 30 trillion cells which are autonomous. Collaborate in groups, have the ability to process information, create knowledge, and use replication and metabolism, conversion of matter and energy. The digital genome provides the specification and execution of a multi-layer network of processes, just as the biological genome does. The digital autopoietic process manager provides the necessary resources to execute system functions. And the digital cognitive process manager integrates a multi-layer network of autonomous distributed processes that deliver unique functions of data collection and processing dependent on the relationships and behaviors associated with each entity. The picture illustrates the role of autopoietic and cognitive network managers. In the context of software systems and the proposed super-symbolic computing structures, autopieces can be thought of as the ability of the software system to continuously self-regulate, self-maintain, and self-replicate its critical processes and components based on its goals, policies, and its knowledge of the structure composed of autonomous components. Each process node takes in information and performs a series of sub-processes. Each sub-process serves a unique function to the entity and relates behaviors of the following sub-processes to form new knowledge structures. Just as a genome specifies functional requirements, non-functional requirements, and best practices and policies based on hereditary history and processes to learn and update knowledge structures. A digital genome based on its specification implements cognizing agents and knowledge structures specifying the life processes of an application with a specific purpose. The life processes of an application are self-regulated through the autopoietic network, which provides the necessary environment and resources to reliably enable the cognitive network processes of knowledge acquisition and model building and its use. The picture illustrates the deployment of a self-regulating application using two different cloud resources. Autopoiesis is a concept that originates from the field of biology and was first proposed by Chilean biologists Humberto Maturana and Francisco Vela in the 1970s. In simple terms, autopoiesis refers to the self-maintaining and self-reproducing nature of living systems. With current technology, we are now able to apply the rules of an autopoietic system into digital systems to create digital automata. There are two main components to achieve autopoiesis within our system. The first is a containerization process like Docker, which provides containerized environments in which each process operates within. Then, a container manager such as Kubernetes specifies the life process of each container by specifying and maintaining the necessary resources to achieve the optimal state as the demands or availability of resources changes with fluctuations caused by external events. Docker enables process replication through container creation. Developers define a Docker file, which contains instructions for building a container image. When the Docker file is built into an image, it becomes a self-contained and executable package. This process of building a container image is akin to self-production, as the container creates or replicates itself based on the instructions defined in the Docker file. Kubernetes allows users to define the desired number of replicas for each application or service. If a pod fails or is terminated, Kubernetes automatically creates new replicas to maintain the desired number of running instances. This self-regulation based on best practices and policies aspect ensures that applications are continually available even in the face of failures. Autopoiesis enables the deployment of reliable services even on a not-so-reliable infrastructure with self-awareness. Kubernetes operates within a self-contained cluster environment. A Kubernetes cluster consists of nodes that host containerized applications. The cluster acts as an operational closed system where Kubernetes manages the scheduling, placement, and scaling of containers without requiring constant external interference. Docker containers are self-contained units that encapsulate an application, along with its dependencies and configuration. Each container runs in isolation from other containers and the host system. This encapsulation provides a clear identity to each container, allowing it to function as a distinct entity. Every process object is containerized into its own API. Each process object is represented as a vertex within a graph database. Each containerized process object API interaction is represented through an edge within a graph database the autopoietic manager initiated. In a structural machine orchestrates the live processes specified in the digital genome. The cognitive manager initiated in a structural machine orchestrates the cognitive processes specified in the digital genome. Please check the references to the left for more information about distributive application development. Schema-based design uses a model of entities, relationships, and their behaviors to perform a network of processes and subprocesses related to each entity. Each entity is constructed into its own containerized process in which receives and sends data related to the object instance in which the process entity is modeled after. These changes are then relayed across the network, updating the state of any dependent entities, relationships, and their behaviors. Each process object is a digital model of a knowledge entity. As information is processed, each action is reflected through the entity's attributes and behaviors within a vertex of our graph database. This allows for a real-time model of changing state and dynamics of the knowledge network and its effects on related entities. As an example of schema-based distributed application development, we have built a prototype to assist with early disease diagnosis. Each entity is represented within a Docker container and managed by Kubernetes. As a user interacts with the system, the cognitive network manager assigns a URL for a container representing the action related to a specific knowledge entity. With each entity interaction, our user is assigned the relevant URL to take actions related to that entity. Each action and interaction is related back to the cognitive network manager, where the necessary relationships and behaviors are established and stored within our graph database. Every change of state is reflected across each relevant network process to serve the most up-to-date information. Each knowledge domain consists of functional requirements, non-functional requirements, best practices, and policies. A digital genome specifies and executes them. The autopoietic manager specifies and maintains the network state and provides resources on demand to achieve a process. The cognitive manager specifies the entities, relationships, and behaviors in a knowledge domain and creates a digital model of each action and interaction of entities. Each knowledge domain has unique processes of knowledge acquisition, analytics, graph database schemas, and user interaction, which relate information back to the cognitive network manager to be processed into emergent knowledge. Within the knowledge domain of early disease diagnosis, we begin our knowledge acquisition with the symptoms a patient is experiencing. These symptom entities are then related to patient information to create a model of patient-symptom relationships. These relationships are then processed through a variety of LLMs to acquire the behaviors of these relationships and hypothesize a possible diagnosis. This hypothesis is then supported through a process of collecting relevant scholarly articles and research to further inform a human specialist who acts as the final validation to incorporate new knowledge into the prediction model. Now for a quick demonstration. As we move through this demonstration, the displayed URL will periodically change to represent a new interaction with an individual entity container. Each entity is represented within the graph on the left. We begin with a medical care provider who will access the system through a verification process and interact with our patient. Now within our care provider dashboard, we are able to select an existing patient through a medical identification number. The medical care provider can then view a patient's information and event history and has established a relationship to the patient entity within our graph database. As our medical care provider assesses their patient, they recognize a series of signs and symptoms that could indicate a disease. Our medical care provider then inputs these signs and symptoms into an input form. There are three main symptoms that the patient has been experiencing: a cough, loss of taste, and shortness of breath. When the medical care provider submits the form, these symptoms are related to the patient within our graph database as symptom entities. These symptom inputs are then processed through our knowledge acquisition node to create possible disease predictions. These diseases are then related to each correlating symptom entity. Now our medical care provider is met with a variety of choices for possible predictions. In this case, they believe the patient may be suffering from COVID-19 as our patient selects their hypothesis. Their selection is ran through a machine learning model based on past data to determine the confidence of their hypothesis through the display of a statistically calculated p-value. This model also returns other possible outcomes if the p-value is less than our alpha of 0.05, as well as other correlating symptoms that exist within our dataset to further inform the care provider of possible disease progression. If our care provider is convinced of a likely diagnosis, they press the button to validate and include this symptom-disease relationship within our machine learning model for future predictions. This validation then triggers a relationship to be established within our graph database between the patient and the diagnosed disease. As our medical care provider continues their assessment, they are informed of new symptoms that the patient is experiencing: bone pain, nausea, loss of appetite, constipation, fatigue, frequent infections, weight loss. These are then added with the patient's previously noted symptoms: cough, loss of taste, shortness of breath. As the system processes this information and makes the relevant relationships to determine a differential diagnosis. This may take a little time. After our process is complete, the medical care provider is able to choose from a collection of possible diagnoses. They are then able to incorporate their personal and historical knowledge to select the most likely disease. As their hypothesis is correlated with historical data, the p-value of the hypothesis is displayed along with other likely disease and correlating symptoms that exist within our historical data. Thank you for your time and attention. This has been our presentation on the general theory of information and machine intelligence. Please feel free to get in contact with any questions.